Hello, in this video we're going to use R to test multivariate ordered alternatives with Follmann's test. Specifically, we're going to look at a simple tree ordering and a simple ordering. And those hypotheses can be represented like this. A simple tree ordering would be like all treatment arms compared against a control arm. And they're called ordered alternative because these are like one-sided tests. So we're saying, is the treatment mean bigger than the control mean for any one of those? So at least one of those would be a strict inequality. And the simple ordering is that they're all strung out like this, that mean 1 is less than mean 2, which is less than mean 3, with strict inequality in at least one of those components. This is a follow-up video to two videos I have where we look at testing all treatment arms against a control arm using Follmann's test. So we really developed the theory behind it. So we developed this test statistic in these two videos. So this would be the simple tree ordering, and this is the simple ordering. And I called it a dose escalation testing using Follmann's because that's kind of what I think of. You increase the dose, so you expect the treatment effect to be a little higher than the lower dose. Now this test statistic is a quadratic form here. It's W, this inverse matrix W, and then some constant out front. We tested at the 2 alpha level, and that's important. And then we look to make sure that these components are positive. W is a transformation of our mean vector. Sig is a pooled estimate of the standard deviation. And for more detail, we can go to this video here. But we'll try to set it up below here. So now let's run some examples, and I want to use the mass library to generate multivariate normal data. We're going to use an alpha of 5, 4 dimensions, sample size of 2. We're going to look at this mean vector of 1 or 0, 1, 1.25, and 1.5. Now we're going to look at the simple tree ordering first, which means we're going to compare each treatment arm with the control. So we're going to assume the control arm is 0, and the treatments are 1, 1.25, and 1.5. So is there enough evidence to say at least one of those is bigger than the control arm? And that's what we're testing. Here we're going to assume that the covariance matrix is this, and see, and this makes sense here. So we have 4 treatment arms. They're all independent. We're independently assigning patients to each treatment arm. So when we take the responses and put it in a vector, the components of the vector are independent, and that's why it's 0 here. But we're assuming a common variance of 16, and that's why it's 16 is down the diagonal. And in the simple tree ordering, remember, we're going to take this mean vector and transform it into something that's meaningful for a simple tree ordering, and that's this. So if we look at this C matrix or transformation matrix, it takes treatment 2 and compares it with treatment 1, treatment 3 compared with treatment 1, treatment 4 compared with treatment 1. Okay, and that's what we're going to do. And we're going to skip the simple ordering section because we don't want to run it right now. We'll come back and do that example in a second. So we generate data. The dimensions of our data matrix is 22 by 4. The sample means are this. Remember, it should be 0, 1, 1.25, 1.5. And that's what it just happened to be. When we transform it, meaning we take treatment 2 minus treatment 1, we get this, and then so forth for the remaining. Our common estimate of our variance should have been 16. It's roughly 14. And that's within expectation. Our cutoff is at the 2 alpha level. That's very important. Numerator and denominator degrees of freedom. Our test statistic is really 2 pieces. The sum of that mean vector, which is 3, and that's positive, and our test statistic, which is 0.9, which is going to be small. Now I like to put this all in one statement. It's an if statement. So if our F statistic is bigger than our cutoff and the sum of that mean vector is positive, we reject. Otherwise, we don't reject. And when I run this statement, it says don't reject. Okay. So now I've set up a simulation. So if we were to conduct this power simulation before we conducted our test, what types of power, what power would we expect? So in this simulation, we use the same mean vector, same covariance structure, and we just conduct it over and over and over and see how many times we would reject. And that's what I'm doing here. So I do it 10,000 times, and the power, I'm guessing, is going to be pretty low, and I want to explain that in a second. Yep, 26, 27%. And the reason is this. I'm going to kind of come back up here to our test statistic. If we look at this covariance matrix, which is right here, it's just highlighted. It's VR, which is our variance estimate, and then C and C prime, or C transpose. And we look at that. It's 35 down the diagonal. We have 17 or 18 in the off diagonal. So there's a lot of variance there. And the mean vector that we're trying to detect is shifts of 1, 1.25, and 1.5, which are actually pretty small relative to all the variance going on in this covariance matrix. And that's why I assumed that we'd have very low power. I mean, we would have to jack this up to a lot to detect these small shifts. I mean, I'm guessing 100 or so. Oh, and we could do that with the simulation below, but I think in the interest of time, I won't do that here. So let's use the same setup, but use a simple ordering. So our C matrix is now this, which compares treatment 2 with 1, 3 with 2, and 4 with 3. And then we generate data, our X, and here's the mean that we generated. So this should have been 0, 1, should have been 1, should have been 125, and this is 1.5, so close. Then we take those differences for the simple ordering. Cutoff, oh no, that's our unbiased estimate, 13. So remember we said the population was 16. Cutoff is the same as before. Here's the two components of our test statistic, the sum and then the F. And here's the one statement to conduct the test, and do not reject, so there's not enough evidence. If we were to conduct a power simulation of what we just observed there, so the same mean vector and covariance matrix as the test that we just conducted, and I'm expecting this is again pretty low. Yep, 27. And here's the reason why. So if we look at the covariance matrix here, now it's a little different. We got one component that's independent, but the rest are all still pretty high. And so that, compared to the small shifts that we want to do. But let's do something where we get we would expect a positive test. So here let's mean vector 0, 2, 2.25, and 2.5. Same covariance matrix. Let's do a simple ordering again, which is we're comparing, the 2 versus 1, 3 versus 2, etc. Generate data, the mean and the variance, or the mean vector there. Unbiased estimate is 14. I'm just going down. Here's the test statistic, and it says reject. So there is enough evidence to assume that there is a simple ordering, or at least one of those two means is bigger than the other. Well, anyway, that's all I have for this video. Once it posts, I will copy and paste the code into the comment section. So if you want to borrow it and use it and enhance it, you're welcome to. And that's all I got for today. I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.